Welcome everyone, and thank you for joining this session on climate impact and circular economy. I will be chairing today. My name is Ruben Vivas, and I'm an economist at the OECD. Alfredo Cisneros Pineda, from the Center for Global Trade Analysis will be hosting today and especially recording the session. Please let me remind you that the presentation will last 20 minutes, and then at the end we'll have a 10 minutes question for each of the presentation. If you wish to ask questions, you can either ask them in the chat or raise your hands and I'll give you the floor. So today we'll hear from three presenters, and please allow me to introduce our first speaker. Jennifer McClelland will be presenting on the economic incidence and interactions of climate change impacts in the United States across regions, sectors, and households. James, yours.
All right. Good morning, everyone. Can everyone see my slides?
Yes. Perfect.
Excellent. Well, it's good to see all of you, even if it is remote. The sun came up a little bit early today, and I was reminded the last time we were together in Poland when the sun was coming up at 4 in the morning. So I guess it's a little bit later in the day for some folks, but glad you could all make it. So I'm going to be talking about some work that I kind of did this presentation, but Mei Yuan, Elodie Blank from MIT, John Riley, and then folks at EPA, Jerry Martin Leach, Marcus Seraphin, and Jamil Al-Salam made a lot of contributions to an earlier version of this. So I'm going to cover some models and methods for introducing climate impacts into the CG model, the US REP model developed by MIT, and then talk about the results and then some possible research extensions. Just a quick disclaimer, the views in the presentation do not necessarily represent those of EPA, and this is more of my personal work. So onto models and methods. So a lot of groups have taken a look at climate damage and impacts in economy-wide models. One of the bigger US studies that came out was by the Climate Impacts Lab under the American Climate Prospectus work. They used the Rhodium Group's MUSE model, which is essentially an implant-based model, recursive dynamic model, and they introduced damages in 7 sectors, so labor, heat mortality, coastal impacts, energy, agriculture, and crime. And one of the interesting results of their work shows the economy-wide impacts are actually greater than the direct damages, and that's what's shown in it's panel D from their Shang et al. Science paper in 2017 that's shown on the right here. And so that was sort of an interesting figure and results. And so we were trying to introduce these results or introduce some of these data to the US REP because we do a lot of this work to look at impacts of climate change. Another big group that's done a lot of work in this area is the JRC, and so they tend to do a static implementation when they're introducing climate impacts into GEMI 3, and they had GDP losses of around 2%, and half of that was coming from heat mortality via VSL. And then obviously there's a lot of great work done by OECD on the Circle project and using E&D linkages, and that showed changes of damage from crop yields and labor supply impacts, reducing GDP by around 1%. So objectives of this study was to introduce the impacts into US REP, and the benefits of this is the work at EPA, we use a lot of models to look at the impacts of climate change. A lot of these models are sectoral based, and so having an integrating framework like the CG model is useful in that we can sort of see a lot of the interactions across sectors. And so this is sort of some initial work to explore that space. So in doing so, one of the big changes to US REP was a disaggregation for a little bit more sectoral detail, going from 12 regions to 29 regions, and also extending the time frame out to 2100 from 2050. We are beginning to look at just 3 impacts: labor, agriculture, and heat mortality. And we're going to examine the magnitude and the incidence of climate damages within US REP across the region, sectors, and different households. So just to describe US REP briefly, originally developed at MIT's Joint Program on the Science and Policy of Global Change. Sebastian Rausch originally worked on this, then Justin Caron, and now Mei Yuan is primarily responsible for the model. EPA has been working with MIT for the last several years to kind of promote and fund the model and fund model developments. So the model includes non-CO2 gases. It goes out to 2100 in about 5-year time steps. It has a vintage production structure. It was originally designed to look at mitigation, and so therefore it has a lot of details around backstop technologies that would come into play if you're trying to reduce carbon emissions. So the methodology, I'm just going to go over a little bit of the work that Shang et al. Did, because these are sort of the inputs to this study. And so we're applying the median damages that they ran, I want to say about 30 different climate models in their study, and we're sort of taking like the median results from there, focusing on 3 different impacts. So the first is labor, and that's shown in the top 2 panels. So high risk labor, you're seeing decreases in labor productivity by up to around 3% in some of the darker areas for high risk labor. And then on the right panel, low risk labor, much less in terms of that. And so a lot of that work was done by a study by Graf, Ziffen, and Nidell. And we're taking those econometric results and then applying that to different sectors in the CG model. We also looked at agriculture. So agriculture, the impacts there are shown in the lower left panel. And one of the unique things about the results here is that you can definitely see a big difference across different parts of the regions of the country. So the Midwest and the South, significantly negative agricultural impacts, whereas in the Northwest, significantly positive results. On heat mortality, again, there's a big north-south divide. So you're seeing a lot of damages and harm due to early deaths in the South. And then you're seeing in the North, you're seeing basically you're actually decreasing mortality because you're lowering cold deaths. I would note that EPA results and some of our sectoral analyses differ a bit from what Shang et al. Report. We don't show as big of a positive impact in the reduction of cold deaths, but that's something we'll be exploring in future work. So caveats and limitations. This is sort of just an initial cut at looking at this. We only looking at the median results. We want to do more to look at the distribution across climate models. The heat mortality in this study, it's more limited than what's in other research. I mentioned that earlier. So the EPA results are a little bit more significant than what's reported here. And we didn't see the decrease in cold mortality that the Shang et al. Study had. And the other issue with this is we're only modeling a single agricultural sector, so we're not looking across different crops. A different version of US rep that provides more disaggregation might have substantially different results. So we're reporting results out at the US National Climate Assessment region levels. And so that's basically 7 regions in the US, 4 regions across the North, and 3 across the South. A lot of the work that we do, hopefully it ends up in some of these assessment reports, and so we've kind of structured the analysis to go along with that. So just to give you a flavor of the level of the shocks, the figure is showing sort of the relative changes in heat mortality and in agricultural output, and then the labor input, so the changes. So essentially, if you look at the Northwest and the Great Plains, you're actually seeing lower mortality levels, you're seeing increase in agricultural output, and then other regions, those tend to be more negative. The shocks to mortality in agriculture are greater in percentage terms than labor. The labor shock is actually generally larger in terms of the actual economic damages. So looking at the climate impacts in US rep. So this figure is just looking at consumption and GDP. And so the levels are pretty significant. So we're just focusing on the RCP 8.5 scenario. It's obviously very, very high concentration levels, but we're just sort of kicking the tires at this stage and wanted to use a scenario where we would actually see some of the bigger changes so we could look at a lot of the interactions, the effects. So in terms of the GDP loss, by 2100 under the RCP 8.5 scenario, nationally you're seeing a loss of about $2.7 trillion. In percentage terms, this equals it's around 3%. Consumption is less than that, so we're not seeing as many impacts by consumption. Agricultural impacts lower consumption by about $200 billion and GDP by about $500 billion. So agriculture isn't as significant. Heat mortality has a much greater impact on consumption than it does on GDP, which makes sense based upon how we've kind of structured that within the model. There's a paper by Riley and Yang that incorporates, when they're incorporating heat mortality, you're essentially assuming that that's somewhat of a loss in utility function. So we're decrementing leisure time. So you're basically seeing lost leisure is how we're kind of counting mortality. To think about deaths from early retirement or deaths to retirees. They're not having necessarily an impact on the workforce, but it is impacting the utility function. So, and we introduce all of the impacts simultaneously. So across the slides, the mortality impacts will be in blue, agriculture is in green, labor is in coral, and the impacts are roughly additive across at least for consumption and GDP at the national level. When we look at the regional patterns, definitely different changes, and this kind of makes sense based upon the initial inputs that we saw from Shang et al. So across the southern region, the Southwest, the Great Plains, and the Southeast, essentially substantial reductions in GDP and consumption. Similar story in the Midwest. The Northeast effects are a bit smaller. Temperature changes there are more muted, I think, than other parts of the country. So that explains part of that. And then in the Northwest and the Great Plains, you are definitely seeing a boost in GDP, less so on consumption, but that's primarily coming from the agricultural channel. And that was kind of shown in the previous input where you're seeing, actually agricultural productivity improvements in those regions of the country. And so they're seeing a bit of a boost under climate change, whereas across most of the country, you're seeing fairly substantial damages. So this is just looking at, then contrasting, the previous figure was looking at GDP changes and consumption changes under RCP 8.5. So if we look at RCP 4.5 versus 8.5, then this can kind of help us contrast how important is the climate scenario and how significant is that. And so, across the board, the effects are much more muted. So the Northeast, there's barely anything detectable, at least on this scale, and the same goes for the Great Plains, at least in absolute terms. The impacts in the Midwest and the Southwest and Southeast under the RCP 4.5 versus 8.5, it's reduced by roughly 50%. And then in the Southern Great Plains, the impacts in 4.5 are about 30% of what the impacts are on 8.5. So obviously, climate does have an effect, but it's still fairly substantial even under an RCP 4.5. So now we want to take a look at how are these impacts across the different sectors. And this is, we're first going to start at just looking at total change in sectoral output. And what we're seeing here is essentially the sectors that have a substantial amount of labor input are seeing significant effects, at least in absolute terms. And so that's across services, other industries, and then energy-intensive industries, and somewhat in transportation. And so this is just looking at the national level. When we look at this across then the different regions, a slightly different picture emerges here. So the same sectors are showing the biggest impacts. We're seeing the largest impacts in the Southeast, the Great Plains, and the Southwest, along with the Midwest. But again, you're starting to see these upticks in output in the Northwest and the Northern Great Plains. And so this is shocking the model with all of the impacts simultaneously. So there are positive positive effects on output in some northern regions, as I said, for agriculture, energy-intensive industries, and other industries. Now, this is just looking at in absolute terms. When we look at the changes in relative terms, then that changes quite a bit. So what we can see here, again, this is shocking all of the sectors, and we're looking in 2100 under RCP 8.5, and the biggest changes are occurring in the Northwest and the Northern Great Plains. So again, we're seeing that big boost in agricultural productivity. We're seeing some broader decreases in output across the Southern Great Plains and across the Southeast. And so, again, those are not incredibly substantial, I guess, in percentage terms, but there is like a broader based hit to the economy. When we break this out by the different impacts, this kind of shows which of these shocks are causing the biggest changes. So the panel in the top left is all impacts, and then if we move down here, this panel, the lower left, is just looking at agriculture. And so again, agriculture, you're seeing increases in the Northwest and Northern Great Plains, decreases across the other regions. You are seeing a slight uptick in natural gas production in the Great Plains and the Midwest. You might attribute that to increases in fertilizer demands. As we look at just the impacts on labor, and so now we're going to the panel in the upper right, the scales change there. So now we're looking at the relative scale is plus 30% to minus 20%. Interestingly, a bump up in natural gas production in the Midwest, and you're seeing declines in the Southeast and the Southern Great Plains. So some shifting of natural gas production. That's probably the largest one. And again, even the labor impacts, you also are seeing changes in the agricultural sector in the Northwest, some boosts in the Northern Great Plains, but then decreases in the southern regions. Mortality is a little bit harder to suss out. We haven't spent a lot of time digging into that. The percentage changes tend to be fairly small. The biggest magnitude is, I guess, in the natural gas sector. And we're seeing some decreases in the Northern Great Plains, some increases in the Southwest. But again, those are relatively small changes. So this is looking at the impacts on household welfare across the regions. And so the labor impacts have the strongest effects on labor. The biggest effects are losses around 2 to 5% in the plains and the southern regions. Counterintuitively, the labor and agricultural damages are not regressive, so the damages rise with income. There's a single labor market in US REP, so we're not differentiating labor exposure impacts by income group. And so that's definitely something that we would want to adjust in the model. So as you have your higher income, you're probably looking at less exposure to labor impacts. So that's definitely something to look at in the future development. The mortality effects are regressive, which makes sense. You're looking at lower income folks are more likely to be impacted by damages due to heat health. So some extensions to this work. There's a lot that we, I guess have done, but there's a lot more that we can do. So I mentioned the CIRA project. So CIRA is the Climate Impact and Risk Analysis Project, and we have reduced form damage functions that were developed for about 15 different sectors at the NCA level as functions of temperature, precipitation, population, and GDP. So these are taking highly detailed sector level models and then doing regressions on those to develop damage functions. And there was a paper published last year in REAP on climate damage functions with Jim Newman, with folks at EPA and Gary Yo. And we took the trajectories in an article developed by in 2017 in Climatic Change that essentially looked at the trajectories of of global mean temperatures across different scenarios, and looking at the 5th and the 95th percentages in temperature change for different changes in temperatures. And in the in the damage function literature, then we're able to essentially estimate not only a central estimate, but then we also have ranges around those damage functions to account for uncertainty in both the climate and then also the damage functions. And so we would like to kind of move that type of a framework into the US RET framework. So that will involve quite a bit of work because we're looking at adding in more sectors, and that would give us the ability to kind of look at climate uncertainty as well as damage function uncertainty.
We have 2 more minutes.
Thanks, Ruben. The second extension would be to introduce even more of these damages from Sierra. And so one of the advantages of the earlier work talked about using these reduced form functions. There's actually benefits to taking the specific damages out of the sectoral model because the reduced form models don't necessarily capture the levels of investment. They're just capturing a dollar in damages, but they don't necessarily capture the level of investment, and they don't always have the regional details that we might like. And to give you an example of this, in coastal adaptation, there's a substantial amount of capital investments that's required to mitigate damages from climate change. And that's not necessarily captured in the simple reduced form damage function. But if we can go back to the data that's kind of underlying the sectoral detail in the model and introduce that into our county-wide model, we could do a lot better job of that. And so just to give you a flavor of some of the key impacts that we're currently missing, air quality is fairly substantial. When we kind of rank the damages across sectors, the labor impacts and air quality tend to be the largest in absolute terms. There's some damage from West Nile disease that can also be fairly important. Infrastructure, that is very substantial investments required to maintain roads and bridges as well as coastal property. The electricity demand and supply, another sector that generally ranks in the top 5 of overall damages when you rank the different sectors for the US in terms of magnitude damages. So introducing that will be valuable. And then we have obviously more to do on agriculture. And then there's also work on coral reefs and shellfish and freshwater fisheries. These things tend to be very small in terms of the level of the magnitude of damages, but they can be definitely important for certain constituent groups, which is why we tend to analyze those. Wildfires and carbon storage, that can also be very important, particularly when we are looking at trying to hit a net zero target. And the wildfires and carbon storage, climate impact can definitely impact the carbon sink that the US has. So analyzing those things will be very important. So I think I'm at time, and that's about all I had. So happy to take questions.
Thank you, Jim, for a very clear presentation. Anyone, if you have any question, please raise your hands or even speak, since we're not a very big group. I actually had a question. You showed the difference between RCP 4.5 and 8.5. I was wondering how much more are the damages muted if you go to, the lower range, the lower end of the
like a
2.6 or even lower. I mean, even lower, I don't believe it, but even 2.6.
Yeah, I haven't run the numbers on. I guess I have the data. I haven't really looked. I mean, 2.6 it becomes pretty low. I think that you see some impacts like agriculture. You still see that shift between the southern regions and the northern regions, but like the labor impacts are muted quite a bit. And one thing I would add while I mentioned the labor impacts, these results aren't out yet, but we've funded Graf Ziffen and Nidell to kind of redo their study with a longer time series of data on the labor impacts. And the labor impacts are looking a little bit more muted. And some of that is because essentially, forward assumptions on the percentage of people working out of doors have changed a little bit. So that's one piece. And then also on econometrics, the damages with the longer time series of data, they don't seem to be quite as impactful. So that's a sector that the damages may decrease, but as we think about adding in these other sectors, air pollution, and then adding in energy and more detail in agriculture, we probably expect those things to go up.
Thank you. Anybody in the audience has a question? Then I may have another question. You also mentioned in your KVATs that you're looking at the median impacts. I was wondering, this way or the other end, how much would the results be impacted by taking, for instance, the higher end impacts?
Yeah. So so I guess I'm going to refer to the Schengen. Also, we almost have the computer infrastructure set up to actually run through all of these different scenarios, but unfortunately didn't get time to get set up for this work. So the Sheng et al. Kind of covers a little bit on how much the damages change. So this is looking at their the science paper from 2017, and this is showing the distribution across the climate models. So for energy, you're seeing the changes are quite a bit in some of the more extreme cases. The labor impacts are a little bit tighter. Agriculture, you can obviously see some, some of the RCP scenarios get to be pretty substantial. So there is a wide range there.
Thank you.
I guess with the work that we're doing, or I guess have planned to do with Gary Yo and some of his work, and these reduced form models. Hopefully, with that, we can take into account, I guess, new climate projections and also uncertainties around those. So that we could run those climate projections then through the damage functions that we've generated, and so that should hopefully provide a different look with a different set of data and different set of models around the uncertainty on climate damages. So we're looking forward to moving that work forward.
Great. Anybody else has a question? Feel free to put them in the chat as well, if you're shy.
So I'm looking forward to hearing the other panelists talk. I will apologize. I have to drop off at 9:30 for another meeting. But, the circular economy is something that we have not yet addressed, but I know we're a little bit behind the times there, and are looking forward to adding those type of feedbacks and impacts from structural models.
Okay. And I guess we can move on to the next presenter. Thank you very much, Jim, for your presentation and your answers.
Thanks for that.
So now we'll hear from, I'm sorry if I don't pronounce your name correctly, Hannu Savolainen, who's going to be talking about from incineration to recycling, an economic and environmental assessment of circular economy for plastics in Finland. Hannu, the floor is yours. You're muted still.
Yeah, sorry about that. It was difficult to find the mute button.
It's great now.
Yep, all right.
And we can see your presentation. Please go ahead.
Yeah, but is it in kind of presentation mode at the moment?
Yes, it's perfect.
All right. Okay, hello everyone. Nice to see you here. So this presentation is about circular economy of plastics, mainly looking at the transition from combusting plastic wastes into recycling and manufacturing secondary raw materials of plastic, and the case study here concerns Finland. This is joint work between me and Juha Honkatukio. All right, a couple of words about circular economy. As some of you might know, it can be seen as a tool for more resource efficient and eco-friendly economy compared to this more or less linear economy from the material point of view. And the key idea is that the value of products, materials, and resources is maintained as long as possible in the economy. And this is something which have been, promoted quite much by the governments and the NGOs and so on. And I think that we in academy and research institutes, we need to address the question as well, since everything might not be as sunny as it is told. Okay, so we need modeling to get idea about the aggregate outcomes, aggregate economic outcomes, and aggregate environmental outcomes when we are talking about the circular economy, because it involves structural changes in the economy. And the waste management is one of the main areas in circular economy, and the wastes are inevitable part of economic processes. So here we are looking at that we should, or there might be point in recycling wastes instead of disposal, landfilling, or incinerating them, and we could use secondary materials instead of virgin materials. Okay, a couple of words about Finland, since we are playing with the model concerning Finland. The plastic wastes usually come from two different sources or two different flows. One is the municipal solid waste, which are kind of, as the name says, it's a mixture of different waste fractions. The plastic being not the most important, but the growing fraction in that mixed solid waste, and also in separate waste flow from industries and households. And in Finland, we have a kind of high garbage mountain to climb here, since there are national and European Union set goals for the recycling of municipal solid waste up to 55% in 4 years, and up to 60% 2030. And in Finland, the current situation is 42%. And concerning plastic packages, the current situation is even more kind of grim. It's 31%. And the national goals, or the European Union goals, are here 50 to 55%. So there's a kind of high garbage mountain to climb. A couple of words about Finland, since I don't assume everybody knows quite a lot about Finland. It's a small open economy in Northern Europe. We are a member of European Union. We have a relative high GDP per capita, and it translates into quite high waste volumes per capita also. Okay, so our research questions here, the main question is that what are the economic and environmental impacts if Finland reaches those recycling goals of plastic waste? So this is a scenario study here, what if scenario. And kind of more precise questions or kind of sub questions are how we can model waste and secondary raw material flows and transactions in CGE model when monetary values are mostly absent. and what policy instruments are needed for secondary raw material manufacturing to ramp up. Then about the modeling approach here. As I mentioned, we are having a kind of a scenario assessment of increased plastic waste recycling using environmentally extended CGE model. The effects are reported of these policies are reported as deviations from a baseline extending to 2040 1-year steps. And the FinH model is a fairly standard recursive Victoria University / Monash-like applied general equilibrium model of Finnish economy, which has been used for many years already. And the current version of the model includes 93 industries and almost 150 commodities. So it's a quite detailed model at the moment. Okay, so how we have kind of approached this modeling work here. So the waste management is rather large industry which supplies waste management services to other industries and households. It supplies district heat by incineration with energy recovery, and it recycles waste and manufactures secondary raw materials. So the plastics in municipal solid waste and in separately collected waste streams can be feedstock for either energy recovery or manufacturing secondary raw materials, which will be supplied to the market. So to ramp up the secondary material manufacturing of plastic, it requires investments, increased collection costs for extended product responsibility companies and other waste generators, meaning services and households, etc. And it also means changes in intermediate use, mostly in waste management sector, and of course this kind of increased secondary raw material output for waste management. And we have in the model there is energy nests for industries, or to be precise, one CES energy nest, and we have differentiated this energy nest for waste management sector to include plastics as one energy or fuel type. And we have estimated since there are no monetary values for this incinerated waste flows, we have estimated the use of or the benefit of this waste plastics for waste management via energy values and prices of alternative fuels, mostly peat and coal in case of Finnish district heat production. And we have also modified the supply of waste management sector, including the secondary plastics under the product group of plastic products. Okay, a couple of words about these environmental extensions. We have extended or included material flow accounting. We have a material intensity coefficients for over 200 domestic imported and exported products, which have been kind of mapped to the product groups of the model. And since there are no material intensity changes assumed in our modeling work, we can report extracted and imported material flows on the basis of monetary values and monetary changes in the scenarios here. And the greenhouse gas emissions is more or less a similar treatment here. We have energy-based and non-energy-based GHG emissions for products, and this work is in progress at the moment, so it's not finalized yet. Okay, then let's look at the scenario assumptions here. We have besides baseline, we have 3 scenarios, and the first scenario includes 4 elements here, which are also included in scenarios 2 and 3. Is that there are these investments to waste management sector, and we assume that the government are subsidizing these investments to make them happen. And then there are this output to waste management sector, meaning the secondary raw materials. We have estimated the value of the kind of maximum output, and then there's intermediate use changes in waste management, electricity and light fuel oil plus 50 to 60% annual, and these are the most important changes or intermediate products which are used in these new plants, these waste management plants. And then there are collection costs to plastic waste generators, and this is the scenario 1. And in the scenario 2, we put a tax on plastic incineration in the waste management sector. And in scenario 3, we put a tax subsidy on domestic plastic products. And this is a more or less similar thing that we put kind of more tax on imported plastic products. And a couple of course, there are the most important parameters here. We have estimated the collected plastic waste amounts or volumes after these circular economy actions. And these volumes are such that in 2030, the goals will be met, the recycling goals will be met. And as I already said, there are revenues from or output from the secondary plastic material supplying, and there are these capacity investments, and these are calculated from the environmental permits of kind of waste management plants already working in Finland. So these are kind of real world data, so to speak. And then there are these collection and treatment costs for other industries and waste generators. Okay, so let's look at the current results. Okay, here we can see that all the three scenarios end up in a kind of a little bit lower GDP compared to the baseline scenario here. And as we can see, the scenarios 1 and 2 are more or less the same. So the tax on the incineration doesn't change almost anything. And you can see that the tax subsidy on the domestic plastic products changes the situation a little bit here. And this already tells us that if there are no kind of markets for the secondary raw materials, or if from somehow or another, if the markets are not supported, if you will, there are not much changes in the waste management sector. So, and let's look at the demand side decomposition first, and then the supply side composition of GDP here. I will focus on the scenarios 1 and 3 since the tax on incineration at the current tax level, or the level of power of tax, didn't change a thing. So as you can see in the first years when the new waste management plants are being built. Of course, there are some positive investments elements, but already the consumption is negative compared to baseline, since the subsidies for the investment subsidies has to be paid, and the government will raise more taxes to make it happen. And after the new treatment plants are working and the new system is working, you can see that almost every element of the demand side is negative here, gradually increasing exports, a little bit stale the situation. And if we look at the scenario 3, meaning the tax on incineration and the tax subsidy, we can see that the situation is a little bit better, but we can see that that foreign trade is taking hit here a little bit more, but the investments are a little bit higher compared to the first scenario 1. Then when we look at the supply side here we can see that, of course, the building phase, the 2 years in the beginning, is more or less a kind of similar than in the demand side, but we can see that the extra costs for the other industries, meaning the collection costs, affect the technology of those industries, meaning that there are more costs, but which doesn't affect their output. So it's a kind of extra burden, and that is the reason why the supply side is taking such a hit here. And when we look at the scenario 3 with the tax subsidies, the situation is a little bit better, and we can see that since there is a tax subsidy, the indirect taxes are so that there's a negative effect on those indirect taxes compared to the baseline. But there are, like there were investments on the demand side, there are capital. The capital is contributing to the GDP here more than in scenario 1. Okay, if we look at the intermediate use of plastics, there are 4 industries. The 3 of those are the manufacture of food products, manufacture of plastic products, and construction are the absolute biggest users of the plastics. And then there's the third one is waste management. And as you can see here, only in scenario 3, when there is a tax subsidy, these industries will react such a way that the imported plastics are, the use of imported plastics are lower, and the use of domestic plastics is a higher than in baseline or in scenarios 1 or 2.
Manu, you have 2 more minutes.
Yep, thanks. And when we look at the impacts on material flows, we can see a kind of similar element here, so that that only in scenario 3 we will see the effect that the imported material flows are lower than in baseline, and domestic material flows are higher, and mostly this comes from the fact that the fossil fuel use is lower, since there are this kind of circular element of the materials happening in the economy. Okay, a couple of words about the results. So the effect on GDP is negative, because there is need for subsidies and there are additional costs, and lower taxes for the government here, and these new value chains can't cover the additional costs. But the effects on material flows are positive, and our hypothesis is that the effects on GHG emissions is also positive, meaning they will decrease, and this is to be modeled. Okay, so there are, of course, a couple of limitations and uncertainties concerning here. When we are modeling these kind of circular economy actions, it requires a certain level of detailedness, and of course we could just say that okay, let's assume just some material efficiency, and let's see what is happening in the economy. But we have to be aware about this, what is actually possible here, but not going into too detailed level. And this is more or less a kind of craft work in a sense. And the tricky part is how to monetize this absent flow. So the input data for the policy scenarios is a tricky one here. And of course, as we can already see in these results, is that the demand and the markets for the secondary raw materials of plastics plays a key role here. So this is something, there's already a discussion going on in Finland that should there be a kind of a requirement to mix up the virgin plastics and secondary plastics to make the kind of create markets here. And the further steps, what we are going to do here is the sensitivity analysis of the tax levels. We have to analyze the results more, identification of winners and losers in some sense, meaning look at the industries and analyze the raw material aggregates a little bit in more detail, and complete the greenhouse gas emissions calculation. And after that, we can make a kind of systematic comparison of economic and environmental effects here, because now the results are concentrated mostly on the economic side. Thank you for your time, and I'm happy to hear your comments and trying to answer your questions.
Thank you very much, Hannu, for your presentation. Again, if you have any questions, feel free to raise your hands or write it in the chat. Yes, Elaine.
Thank you. Thank you for your presentation. I was wondering a bit, because I'm assuming that in all your scenarios you are reaching the recycling goals that you set, or not? So why are not in all the scenarios the industries using the domestic recycled plastics? Sorry, because I saw that only in the subsidy scenario you really start using it.
Yeah. Yes. Thank you for the question. I think the most important thing is that there's a kind of the relative prices are such that it's the unit costs are lower in imported plastic products compared to the domestic plastic products. And this is our analysis at the moment, and this is why it doesn't happen. The use of the domestic plastic products doesn't ramp up if we don't change the relative prices here.
Okay, thank you.
Thank you. I see the next hand is Maxim.
Yeah, thank you for the presentation. So I have two quick questions. So the first one is, you mentioned the issues that you faced in terms of the representation of the secondary plastic production in the IR framework. So my question is, what source of data or assumptions did you use to represent the cost structures of the secondary plastics production in your model? And yeah, I can also, maybe fill this question and then I can ask the second one.
Okay, yeah, thank you for the question. we changed the kind of cost structure or the intermediate use of the waste management sector on the basis of what the companies have reported when they have applied to environmental permits for their plants. So they have listed what are the kind of most important raw materials they need to use to make those plants run up and running. And otherwise, we have just assumed that the cost structure of the sector will stay intact. And of course, when they are ramping up the production, they will use more of the electricity and the light fuel oil, like I mentioned, but also they will use more the other intermediate products here. So this is once again a kind of balancing that we just need to assume that there are similarities, but we want to add those most important intermediate products into model.
If I may, Maxim, I have a clarification question on this. I didn't quite understand. Did you mean that you're separating the waste management sectors into two? One it's regular? Okay.
No, because the waste management sector already includes different kind of waste pre-treatment plants and kind of mechanical recycling plants and those incineration plants. So we see a kind of mixture of intermediate product use already, and we just add accordingly to the investments we increase the certain intermediate use in the data.
So if I may rephrase, but to make sure I understand, you force the technological coefficient saying incineration is going to go down from, I don't know, 30%, I don't know how much it is, to 10%, recycling going up from 30 to 50, and that's going to change the inputs.
Yep.
That's what you do. Okay.
Yep.
Thank you. That's clear.
Yeah, correct.
And you didn't change technologies between primary and secondary production? No. Okay.
No.
Thanks, Maxim. Sorry, I just didn't quite understand.
Yeah. Okay, sure. And the second quick question is in terms of the actual policies in Finland that are implemented to stimulate the recycling and secondary production of different materials. So you model some specific policies based on your assumptions like subsidies but I was wondering what actual policies are planned or already being implemented in Finland to essentially stimulate the move from primary to secondary materials. In the sense that maybe in the longer term, it might be also relevant to try and capture kind of like these actual policies if it is possible in the model.
Yeah. Thank you. A very good question. At the moment, the most important thing is concerning the plastic waste flows is the extended producer responsibility, meaning that the companies need to set up a kind of separate collection for plastic packages, and this is a kind of voluntary for the households, but they are setting up the system, or they already have set up the system. But as we can see, at the moment, the recycling rate is only 31%, and under the discussion are the tax on the incineration, waste incineration, and then this kind of mixing the virgin plastic raw materials and the secondary plastic raw materials in the production of different plastic products. So these are the two under discussion here, and there might be also some other and what we could try here, but maybe the basic setting here is that since there are not enough treatment capacity in Finland at the moment, we assume that there needs to be some investment subsidy to reach the kind of level. It might also happen that we just government just says that that you need to ramp up the recycling rate, or you face some what is it, kind of economic consequences, so to speak, or like that.
Thank you.
Thank you. The next question is from Eleonora.
Hi, thank you very much for the presentation. I have two quick questions. One is the data behind the investment cost for incineration and collection of waste. Is this field specific, or what is the source? As well as how do you decide the level of the tax on incineration? And the second question was to do with the substitution. You mentioned that there will be a substitution of materials, of plastic with other materials, and if you have an overview of which materials it's being substituted with, and that would be important to see what are the environmental impacts. Thank you.
Okay, unfortunately, I couldn't hear the first question, so could you repeat it, please?
Sure, sorry. The first question was to do with the data sources, for what are the data sources for the investments, and for the tax on incineration.
Yep. Okay. Yeah. So the data sources for the investments were all they were kind of from these environmental permits and from kind of these annual reports of the companies in Finland. There are a couple of which have invested on these plans, so there are quite of recent data for that. And about the substitution, this is a more or less tricky part, because we didn't differentiate the kind of virgin plastic material products and secondary plastic material products. And I think that would be the most feasible or the best way to do it. So this is a kind of initial step to see what are the modeling results when we are just assuming that there are this waste management sector produces plastic products, and see what is happening, and they have the option that they will incinerate the plastic or they will supply the plastic products here. But to make it really a kind of nice modeling, I think it would be best to differentiate those product groups, and then set the kind of substitution or some elasticity between those product groups.
We're out of time for questions. Maybe to move on to the next presentation.
Yes. So thank you very much, Hannu, for your presentation and your answers. The next and last presentation will be from Helen Barklings from Wageningen Economic Research, who will present on waste management and circular economy in a CGE framework. So yes, I will see your slides. Helen, you have. You need to unmute yourself. We can't hear you.
Sorry, can you hear me now? Yeah, okay.
Yes.
Thank you. I'm Helene Bartelings, and I will be presenting the paper called Waste Management and Circular Economy in a CGE Framework. And this is a paper in which we describe how we implemented a waste treatment model in NECT. And my presentation seems to be frozen. Yeah, okay, now it works. This is a short outline of the presentation. First, I will shortly introduce Magnet, which is our CGE model and which we use to analyze this new waste module. Then I will discuss the model changes that are needed to include the waste module. I will discuss the data that we collected to get the new model up and running. And then I show some baseline results from a simple SSP2 baseline, just to show what you can expect of the new module. And finally, I will go into some future scenario analysis that we are planning to do. First, magnet. Magnet stands for a modular applied general equilibrium tool. And this is a global economic model which is based on Gtap version 7. It has a modular setup, and that means that we can include or exclude modules depending on projects. We also have added quite some new sectors and commodities. So we added also some standard code to include new sectors and split out sectors from the standard Gtap sectors. We at the moment have about 130 regions and about 125 commodities in the model. We run mostly scenarios from 2014 to 2050, or when we're looking at greenhouse gases and climate change up till 2100. And our model is, of course, used by ourselves, Wageningen Economic Research, but also by JRC and Thune Institute, and we had several projects with FEO and the OECD. This is are the Q and models in the magnet model. So like I said, we have a modular setup, so we can, depending on the project, turn these modules on or off. So we have quite a number of modules that are focused on the bioeconomy, some on nutrition, some on agriculture, but for this presentation it's important, the green side is important, namely the new module which deals with waste collection and treatment. Here I show the system that we set up to include waste in magnet. So we are looking specifically at household waste, so municipal solid waste. And we have households generating waste, and they can generate at the moment 5 types of waste. So we have food waste, garden waste, paper waste, glass waste, and other waste in the system. And the type of waste that is generated is important because that also will determine how it can be collected and how it can be treated. So food waste and garden waste, if it's separated, can be collected as green waste. Paper waste and glass waste can be collected as paper and glass, and other waste can be collected as grey waste. We also added the option that because separation rates are not 100%, certainly not in the base data. So food and garden waste and paper waste and glass waste can also be collected as grey waste. Then we added waste treatment. If the green waste is collected, then it can be sent to the composting unit and can be composted. If paper and glass is collected, then it can be sent to the recycling unit. And if it's collected as grey waste, it will go to final disposal, which is landfill and waste incineration. And then we also added the use of secondary materials in the model. So composting produces compost or biomass, and that can go to the crop sectors as a biofertilizer, or it can be used in the second generation bioeconomy sectors, which is bioenergy, secondary generation biofuels and biochemicals. If waste is recycled, it will produce recycled materials, and that can be used in the paper industry or the glass industry. And finally, if waste is incinerated, it will produce energy, which can go to the electricity sector. And landfill is really the only waste treatment system that doesn't have any secondary materials or energy produced. Like I said before, we have households generating waste. And we found it very important that there is a direct link between producing waste and consumption. So if a household consumes more, they should produce more waste. In the Gtap 10 database, waste collection and treatment is included in the WTR sector. And if you make it a separate sector, then there is no connection with consumption of other products. And therefore, we have chosen to include waste as a margin commodity. And for this, we follow the method that is used in the Gtap M model and was presented by Peterson in 2006. On the right-hand side, I just show the demand function. And the white cells are the standard Gtap demand functions, and the green cells are what we added for domestic margins. And what it means is that, so we have a product, consumers will always buy a bundle. So they will buy a product and then immediately also buy the collection of that waste and the treatment of that waste. So, for example, if we look at here at VMBA, so VMBA is the basic price of a good, and then we add a waste collection margin on top of it, the MRHB, and then we get the bundled commodity, which includes both the price of the commodity and the waste collection cost. Then we add consumer taxes, then we get the producer price, etc. And then finally we get to the demand again. To get the new system working, we needed to have a lot of extra data. So I want to go briefly in the data that we collected. We use mostly as a source the World Bank database. We also use a database from EU Fusions projects, which specifically looks at food waste. We use cost structures which were published in an European Commission report, and we use emission data from IPCC. So we needed to collect data about waste generation and specifically the composition of waste. We collected data about waste collection, and we collected data about waste treatment. First, so the World Bank publishes data of total waste generated, and they use as their starting point 2016. And the Gtap database is on 2014, so we rescaled the data from the World Bank by taking the municipal waste per capita and just multiplying it with the population in the Gtap database. And then you get the following picture in the base year. So you see that a lot of waste is produced in the developed countries, and the developing countries are still producing less waste. The waste composition is shown on the right. And we see that there is also for the waste composition of municipal solid waste, there's a lot of difference between regions. At the moment in Magnet, we only take into account the food and garden waste, the paper waste, and the glass waste and other waste. So the other waste streams like metal, plastic and rubber are for now left out of the equation, but we want to include that later on. One thing that was quite important and where we couldn't find any data is attributing the waste generation to consumption. We don't have a worldwide material flow database available. And when it comes available, we really want to replace these assumptions because they are quite big assumptions. But for now, we attributed waste to consumption based on the Gtap intermediate expenditure data. And the idea behind is that if a lot of, for example, for paper, if a lot of paper is used to create a product, then a lot of paper waste should be produced when the consumer is consuming this product. So for glass paper and green waste, we calculated weights based on the intermediate expenditure data. So in the top right figure, for example, we have the shares of paper and glass which are used in different aggregated sectors. And for example, for paper, you see, so if a consumer will consume something from agriculture, only a small amount of paper waste will be produced. However, if they consume something from the paper industry or the manufacturing industry, far more paper waste will be produced. And if we apply these weights then to the total waste generated by category, we get these kinds of shares of the different waste types while consuming a product. Another thing that is good to take into account is that not all waste that is generated is actually collected. So in the picture in the left-hand side of the slide, you see the collection rates around the world. And again, what you see is that, for example, in North America and Europe and Asia, a lot of the waste that is generated is also collected. So we see percentages over 90%. However, for example, in Africa, the percentage of waste collected is lower than 50%. And at the moment in Magnet, we do not account for dumping. So we assume that if waste is generated, it is also collected. And for countries that do not have a full collection rate, we scaled the waste generation data down. Also in the base data, we also see that a lot of the waste that could be composted or recycled is at the moment not collected. It's separately. It's collected as res waste. And that means that it will not be available for recycling or composting. So certainly in the base data, that is a lot of things to gain if proper waste management policies would be implemented. Finally, we collected some data about waste treatment. We have the waste treatment in kilograms from the World Bank, and they also published some data about prices, which we use to calculate the values. And then we did a literature search on finding cost structures for all the new sectors, and we implemented those cost structures. So that was all the steps that we needed to do to get the model running. And then we wanted to test it in a simple baseline to show what you could expect with the use of this new module. And in this baseline, we simply assume that there's an SSP2 development, GDP, and population. And we also took into account simulations that the World Bank published. So they published a link between GDP and waste growth. And we implemented waste shocks to make sure that we followed the same development. Then in the baseline, you see these results for the amount of waste that is collected in the period 2020-2050. You see that in all regions of the world without any waste management policies, waste will increase quite a bit. Especially in Africa, the growth rate is very high. Then we started zooming in on Europe, which was the focus of our study. And here we show in a Sankey diagram how the waste flows work in the model. So in 2050, without any waste management policies, this is what you can expect to happen in waste in Europe. So on the left-hand side, you see how much waste is produced by consuming different products. And then you see which kind of types of waste this will be, how it will be collected, and how it will be treated then. And then also how we can link CO2 emissions to the treatment of waste. And what you see for Europe is that about 50% of the recycled waste, of recyclable waste, will actually be collected as glass and paper and will be sent to a recycling unit. And about 30% of the food and garden waste will be composted. And still, so a lot of the waste, even the recyclable and compostable waste streams, will still be collected as res waste and sent either to an incineration unit or to landfilling, where we see that landfilling has a disproportionate impact on greenhouse gas emissions. That was a total overview of Europe, and of course for the different countries in Europe, not everything is similar. So if we now look at the volume of waste treatment, well, we already know that waste increases, and this the biggest increase is in incineration and landfilling. but also recycling and composting do increase a bit. What we see is that, for example, Germany already in the base data has a very large percentage of waste that is incinerated and very low percentage of landfilling. It's the same as for Benelux, for example. And this trend continues, so they will incinerate more waste. Especially for the rest of Europe, the landfilling is still quite extensive, and will even increase quite a lot by 2050 without any policies. Then we can also zoom in on green waste. So, for example, here I show how the green waste stream is can be divided in food waste and garden waste, and how this is expected to develop in 2050, given changes in consumption. And of course, changes in the growth of GDP. And if waste is composted, it will produce biomass. And this biomass can be used in the crop sector as biofertilizer or in the bioelectricity sector mainly. And what we see in 2014 is that really almost all waste is used in the crop sector as a fertilizer. However, in 2050, the demand for energy increases a lot, and it gives opportunity for bioelectricity. And since bioelectricity is limited with available residues in the model, it is for them interesting to start using more compost. And what we see if we don't limit this in any way in the baseline is that a significant amount of the compost will go to the bioelectricity sector in 2050. If we look specifically then to the crop sector and the bioenergy sector, we see that even with the extra use of compost, the food waste grows so much that biofertilizers will still grow. And so without any policies, it can be expected that some of the fossil fertilizers are substituted with biofertilizers. And for the bioenergy, well, it started with almost zero, and in a lot of countries in Europe, it does become cost effective, and the bioenergy sector does start using compost. Finally,
some more minutes.
Yeah, well, that's good.
Okay.
This is my final slide. So I wanted to go into some policy questions that we want to start answering with this model. Because we have now modeled waste from cradle to grave, we can also start mimicking interventions at every stage of the waste stream. And what we are now looking into is trying to analyze something like consumer waste reduction, and specifically the impact of food waste reduction. And we will also want to start looking at the impact of, for example, rest waste collection, taxation, or subsidizing green waste or recycled waste collection, or look into impacts of subsidizing recycling, of composting, or even use of biofertilizer in the crop sector. And that was what I wanted to present today. Are there any questions?
Thank you very much, Helen. It was a quite interesting presentation. I see that Dominique has his hand raised. You want to ask the question? Your question?
Great presentation, Helen. I'm always impressed with the quality and the depth of the work done at Wageningen. I have two questions. One is obviously putting on my Gtap hat. Is the data that you use to calibrate the model, is that done at the fully disaggregated Gtap level? In other words, could we use that database to re-aggregate to a different regional aggregation for modeling purposes?
Yes, it's all the database calculations. So I didn't show that in the presentation because I can't get that in graphs. But everything is done at a fully disaggregated level.
All right, Maxim, you have your work cut out for you. The second question is, and this really relates, I presume, mostly to the high-income countries, but increasingly to developing countries. I'm thinking particularly of food waste. I would think a large share of that is coming from the service sectors, and it seems like you're not capturing that. Is that correct? I'm thinking of restaurants and grocery stores and
Yes, no, we did include the service sector. So we don't attribute a lot of waste to the service sectors, but food waste is indeed attributed to food services.
Okay. Because I was under the impression you were just looking at household demand and waste, no?
Yes, but we did take into account indeed. Let's see, where it is. So we did assume that if households consume food services, they do produce waste to get that quite important waste stream for food waste into the system. And the same is a bit for garden waste, because we needed to attribute that somewhere, and we chosen to attribute garden waste to dwellings. So we wanted to also have a link there with the consumption of a commodity.
All right, I'll have a deeper look at that. Thanks.
Thank you, Dominique. The next question is from Maxime.
Yes, thanks, Helena. Really great work and very interesting. I have a couple of comments and then also some questions. So in terms of the comments, you mentioned that in Gtap, recycling and waste treatment is captured in the water sector, which is as based on like IC classification. But we recently also were doing some work on some secondary production splits, and when we compared the actual values of, let's say, scrap produced by iron and steel and then treated in waste and then fed back to their iron and steel production, we found that like in Gtap the waste, the water value was like underrepresented between 100 times and more. So essentially, in the actual IO tables, it seems that this scrap value is not in the water sector. So, I mean, we ended up disaggregating it from the corresponding primary sector because otherwise you can't really like get the values that you need. Like, if I recall correctly, like in US, it was 150 times underrepresented, like the value itself. If you look into the intermediate use of water by, let's say, primary steel production. And of course, if we would add up all other activities, I assume it would even worsen the situation. So yeah, that's one point I wanted to raise. So then one other question I have in terms of the recycling rates. So as far as I'm aware of the World Bank database, they do not report recycling rates by countries. So you know the waste, but the value of waste, but for instance, you don't know how much plastics is recycled in Zimbabwe or like in China. So that's really a very country-specific data. So I did not quite get from your presentation, how did you address this this issue? And also on one other point on the recycling rates, as far again as I understand from the World Bank database, it's pretty aggregated. So, you know, it can be a very different share of waste that comes from vegetables, fruits, and nuts, and from rice and from wheat. And the World Bank just reports an average rate, which might be 80% for one commodity and 10% for other, but World Bank would report 25, like also aggregated. So there is a lot of heterogeneity in both of these kind of aspects. So I was wondering, how did you approach this point?
So first about the recycling rates. Yes, I didn't mention that, but that is something that we got from a different study, which at the moment I can't just think of, but it is mentioned in the report that we are writing. But yeah, indeed, so the recycling rates do not come from the World Bank. And in some cases, especially for the composting sector, we did need to make some assumptions there, because I think for the composting, we only had data for Europe, and we extrapolated that for the rest of the world, which is, of course, very rough, but yeah, we had to do something. Sorry, what was your first question again?
So in terms of the aggregation bias, in sense that World Bank reports a very aggregate groupings, yeah?
Yes,
then you
of
need
course,
to
yes.
map it to Gtap, and definitely both the waste rates and recycling rates, they vary significantly by commodities. So yeah, my question was, how did you address this point?
Yeah, so we didn't notice actually, because we only focus on paper and glass waste, so we didn't have. So I looked at the ISIS codes, and I thought that everything was indeed included in this water sector, and we didn't have problems splitting it out. So I assumed that everything was correct. The only problem that we did have is that for the energy from incineration, there we couldn't assign all the energy that we calculated that there should be. Because not enough of the water sector was going in the electricity sector, there we did some adjustments actually to the data to make it fit.
Okay, and agriculture, I was having in mind agricultural waste, or did you took it from any other source in World Bank?
So we, you mean the use of fertilizer in agriculture, or because so here we don't look specifically at agricultural waste, only household waste. But if I checked indeed how much we calculated that they should be using by compost in the agricultural sectors, we didn't have any problems there that fit the database.
Oh, well, for instance, households buy apples, yeah, and then there is the waste of apple. They also buy meat, so there could be some waste, yeah. So there is a different waste from different food commodities. And I was just wondering how you address this. Yeah, sorry, maybe I did not. Yeah. Mm-hmm.
So that is something that we actually. So what I presented in that we made. So we only take the aggregated levels from the World Bank. And the World Bank just reports indeed food waste and garden waste. And we attributed this to different agricultural sectors based on expenditure shares. So we took so the primary agriculture use in different sectors, and that is what we use to calculate the expenditure shares of food in different sectors.
Thanks for clarification.
And so we also, because the World Bank only publishes data on food and garden waste together, we also did some work on splitting that, because food waste is a very important subject for a lot of the analysis. So it's something that they really want to address. So we really wanted to have food waste and garden waste separately. And there we used the data that, so for some countries, the World Bank does publish it separately. And we also had data from the European Union that published it separately. And then we used a world average to calculate it for the rest of the world.
Thank you. Does anybody have a last question? I had a quick question on the data that you use, if I may ask.
Of course.
You mentioned that you're gathering data for treatment costs. I imagine, per ton or per kilogram.
Yeah.
Do you remember where you got the data from specifically?
And we got most of the data from an European Commission report, which was quite old, but it was the best that we could find. And I'm just looking it up.
We have the same issue that there's not a lot of data on this.
Yeah, so we got most of the data from RDC Environment and PR International 2003. So they have quite some extensive cost structures for different waste treatment and recycling options.
Thank you. Okay,
I think
so it doesn't. Yeah.
Maybe one quick question, and there, you're working on the report you mentioned. Is there any estimate when it will be forthcoming? Because I mean, it's definitely much of an interest for the community.
We are finishing it now, so we hope to have it finished actually beginning of next month.
Oh, great.
So it's really in the final stages at the moment.
Okay, we'll note it here.
Okay, so thank you, Helen.
I see your boss is laughing, so I'm not sure why. Okay.
I noted it down, Dominique. So Elaine, nice to get it.
Yeah, Hans asked me to ask this question. Yeah, so.
All right. Seems we're about done with questions. Thank you, Helen, for your presentation and answering the questions. This wraps up our presentations and discussion for today in this session. Please help me in thanking all the presenters for their valuable contributions, and we appreciate everyone joining us. And I wish you a nice rest of the conference.